made a major impact with its penetration in the grid, but at the same time, there's a lot of thermal around. How we increase the renewable penetration to a larger extent, what new innovative technologies we can inbuild, how flexibility we can build into the grid, and overall achieve carbon reduction. Today we have esteemed set of panelists. We have people from BPCL, we have people from Red Stack, where we will talk about different technologies and automation process, where expansion of renewable power can be more possible and can be tried in a larger scale. So I'll quickly introduce you to the panelists. We have Anthony Savio from BPCL. He's Chief Manager Power and Utilities. We have Peter Hack. He's Chairman Red Stack Energy. We have Nick Boriso, VP Business Development River Capital. And we have Nitish Kumar, Lead Application Engineer from GE Vernova. Go ahead, give a quick brief about yourself and give the presentation on.
Good afternoon all. I'm Anthony Savio. I am Chief Manager from BPCL Kochi Refinery, basically looking after the captive power plant and the energy procurement for the refinery. So my topic here is how we can maximize the utilization of the renewable power using an automatic power or power factor controller in the generators. So this is the content. After having a brief introduction about the organization, we'll discuss about the power scenario, typical power scenario within a refinery, and how the renewable energy sources are penetrating to the existing power basket, and what is the constraint in the maximizing utilization. Then we come to the solution of what we have implemented in Kochi Refinery. So why there is a shift to renewable? It's a global warming. Everyone knows about this one. You might have the temperatures going on. I am coming from the southmost point of India, where there are backwaters, and in the high tide time, we are facing that the water is coming to our courtyard. So it's a need of the time that we must arrest this global warming. And in this line, our country has committed for the net zero. And as a BPCL, we are also committed for net zero by 2040. So while going to the net zero and we are reducing the fossil fuel, we have to sustain the industry, because the industry should be able to run, because these new renewable energies are yet to maturize. So my topic is on optimizing the resources while we conserve the environment. Just a brief on BPCL. It is a Fortune 500 company and is the fifth largest company in the country. We started our journey in 1928 as Burma Shell and was nationalized in 1976, and in 2017 became the Maharatna company. I'm coming from the Kochi Refinery, which is the largest PSU refinery in the country. Coming to the power scenario of Kochi Refinery, actually we are having a 175 megawatt load, which were supplied by the gas turbo generators, GTGs, in the refinery, as well as a PRT of 10 megawatt. The remaining power we are taking from the grid, that is 25 megawatt we are taking from the grid. This is prior to the greening. And when the renewables came in picture, we installed 13 megawatt solar power plant, and we started buying power from the GDAM, or Green Day Ahead Market, that is available in the country. Here, the green energy is generated somewhere in the country, across the country, and it is available in the open access network, and through the existing grid, we are taking this power to the refinery. Also, we are having the 30 megawatt solar, and this is how the KRT is taking the green energy through the open access. There is a Green Day Ahead Market. So we will bid for the energy 1 day in ahead, and a day is divided into quarters, and there are 96 quarters per day. So we will bid for each of the quarter, and the allotment varies from quarter to quarter. So once the energy is allotted, then you have to give the money 1 day ahead. So if you don't take the energy, that energy is lost, or your money is lost. So this is the green energy that we are taking from the open access. And in parallel, we are having a solar power plants, 5 plants with three major ones as shown here. So this is the typical solar production. It's somewhat like a normal curve. Normally, it will start something around 6 a.m. and peaks at 12 p.m. and it comes down at 6 p.m. But this solar is connected to the grid, and you know that the grid is an uncontrolled source of energy. Means, if you are having an import of 25 megawatt at the say 6 a.m., when it comes to the peak, your solar production will go to 13 megawatt, and the grid import will go to 12 megawatt. So if you have bought the energy for 25 megawatt, then you will lose the energy, or you will not be able to utilize that green energy that you have bought in the afternoon, in the mid-noon, because your solar production is high. And when you're taking an typical case of Kerala, Kerala is having wide solar variation, wide variation in the solar irradiation because of the presence of the cloud. So the solar production will also vary. So you can't see a normal curve anywhere in the Kerala for the solar production. In such scenario, there is a fluctuation of the solar power from 1 to 10 megawatt to during the daytime, and we have a minimum obligation to take from the open access. So we need to maintain the KCB or the state utility load at the minimum threshold, and this load adjustment we have to do in the in-house generator. So this is, if you are doing it through a manual control, then there is a continuous monitoring of engineer is required, and this precision you will not get. So for this solution, we have joined up with our ECS provider, that is Emerson Process, and we work together in the Global Engineering Center in Noida, and we have developed something called as the Megawatt Controller Module. Here in the Megawatt Controller Module, the KCB or the state utility load is adjusted by adjusting the gas turbine dynamically. It is operated through the ECS and adjusts the GT load on the real-time basis. Actually, the ECS controller logic is not controlling the generator, but we are sending a 4 to 20 milliamp signal directly to the controller of the generator, and the turbine controller does the actual load variation. So it's something like this one. The ECS acquires the active power from the grid, and it will give the control directly to the generator governors, and it allows the operator to set the grid load parameters and control generators. So now the modified one is like this one. If the 25 megawatt import was there, and there is a 140 megawatt in-house generation is there, when it comes to the peak of generation, it goes to 13 megawatt solar production. The import will be maintained at 25 megawatt itself, whereas the in-house generation will be reduced to 127 megawatt. So the other advantage of this one is that the ECS will maintain power adjustment with the generator capability limit. Next thing is that it ensures safe and efficient operation under varying load condition and safeguards the operational integrity of the refinery. One more thing what we have implemented is the grid power factor controller. For a non-electrical guy, you see there is two parts in electricity. That is, one is an active power and a reactive power. So all the solar generator is having nil reactive power. The reactive power from a solar power plant is 0. So the in-house load and means the active power and the reactive power will continuously vary, and hence the ratio of this is denoted by power factor. That power factor will also continuously vary. So we have introduced one more thing, that is the megawatt module controller module, and our state utility will give incentive for maintaining the grid power factor at unity. Here also the megawatt controller will monitor the power factor at the point of coupling, and it will adjust the generator reactive power so that it will maintain the power factor at point of coupling at unity. So this is a graphical representation or the screenshot of the ovation module, which is controlling the generator megawatt and megawatt, and this is a control desk. And you can see that the generator is within the capability curve. So here this solution is for the transition period. This is for the practical period in which there is a transition from the fossil fuel to the renewable energy while handling both, while maximizing the renewable energy source. I thank this organizers for giving me the opportunity to give a presentation. Thank you.
Thank you, Savio. It's a very interesting presentation. I have many questions myself, but as the instruction goes, I cannot ask. We'll connect with you again. But can I now request Mr. Peter Hack, Chairman Red Stack, to come over and present on options towards net zero salinity gradient power.
Good afternoon. My name is Peter Hack. I'm a founder of a Red Stack company from the Netherlands. I have the honor to introduce to you today our technology for generating full sustainable power out of contacting a flow of fresh water and salt water. I'll talk about the technology that we have developed, of the experience so far at the pilot plant, why we choose to come to India as one of our focus countries, and of course what would be the potential to apply in India. In the meantime, I also give some background on the ecological effect and of course the financial consequences of using this type of technology. How does it work? We use a flow of fresh water and we use a flow of salt water, and we combine them in our equipment in the membrane stack, and there the salinity, the salt wants to equalize from salt into the fresh water. And by passing through the two different membranes, one for the anions, one for the cations, we generate the potential. The retention time of the water, the fresh water and the salt water between the membranes is only 10 to 15 seconds. We generate about 50 millivolts per membrane. Yeah, 50 millimoles is not a lot. But when you make a stack of a 2000 membranes, which is the present design, we generate 100 volts DC on a continuous basis. And as long as the water keeps flowing, we generate this potential. And it is DC, so it would be very nice to immediately use it for hydrogen electrolyzers or to feed server centers. And as long as the river water flows and it meets the sea, it generates power. Of course, you also can use other flows of fresh water and salt water. For example, the brine from a desalination plant. This is very salty water, normally spoken discharge. And for example, as a freshwater source, treated municipal sewage, which might be flowing into the sea. And also in industrial areas, some other either brines or freshwater flows are available. The potential worldwide, you can calculate on that. We did it ourselves, but also used the data from various universities and institutes all over the world, and counting each and every river, and then really counting only the full continuous availability. So using the low flow in the dry season of the river. The worldwide potential would be 3.2 terawatt full continuous. In Asia, 1 terawatt. And in India, we come up to 114 gigawatt as our first calculations. The company officially was founded already back in 2004 in the Netherlands, but to be honest, in the first years, we didn't do so much. We were waiting for the scientific results from the Wetsers Institute, the Netherlands, to prove that the technology works at least at laboratory scale. And it took all the way to 2011 before the PhDs at the Institute proved, yes, we can meet the data as we came out of the model. So then we started constructing our pilot plant, which was commissioned in 2014. And we are very happy and proud that our King Willem-Alexander from the Netherlands, came to do the ribbon cutting ceremony and at the grand opening. Later, we also got many visits, for example, from a Prime Minister from the Netherlands. We were awarded the title of a national icon by the Dutch full board of ministers meaning that we are solving a societal problem in an innovative way and in a cost-effective way, good for business, and hope to materialize on that. End of last year, we were to get a new round of finance injection in the company, meaning that on the one hand side, we will now be able to expand our pilot plant in the Netherlands to a bigger capacity. From TRL7 go to TRL8, and making the membrane stack into the full final size. So far, we did upscaling from a membrane stack from a small one with a quarter of a square meter membrane only to a nice size one, 250 square meter. Now we will go to 2,000 square meter of membrane in one membrane module. This will be having a diameter of 1 meter, a length of 2.5 meters, and depending on where you will operate it, it will generate between 3 to 6 kilowatt per membrane, per module, sorry. We also have started investing in automating the production, assembly of the membrane stack as a first step in the cost down, and of course in increasing the capacity of our company. As I just said, we have a pilot plant operating in the Netherlands, which you can see in the main picture. On the left-hand side, you see the fresh water, which is coming from the River Rhine, it's a lake. And at the right-hand side, you see the salt water, the Waddenzee. I come to that later, because this is a very special site with very strict limitations, but I come back to that later. Our second pilot plant is running in Spain, where we're not using surface water, but we're using the brine from a desalination plant, and the fresh water is the treated municipal sewage. They're pretty close to each other, so it's easily combined. Such a plant might not be hundreds of megawatt size, maybe only a few megawatt size, but as we call it, is behind the meter for internal use of the companies and just an add-on to an existing infrastructure, so very easy to get a license and also the project realization not too complicated. The picture below is a bunch of these membrane stacks. In this case, there are 8. As an example, how at the end of the day our product will look. What are the main advantages, what we think that is full continuous, round-the-clock energy. Compared to solar, wind, okay, there is no wind, no sun, no power. As long as you dimension our plants on the low flow at the dry season, low water flow, you always have full continuous energy. And later, when we come to the price per kilowatt hour, please take in mind that you do not need batteries to add on to this technology. So far so good on our pilot plant, operating now for about 3 years at design capacity on a continuous basis. And in the beginning, of course, when we started, we had a lot of troubles with the clogging and everything that could go wrong. But nowadays we can say that the stacks as are operating now are after 3 years still doing the same performance as they were doing after 3 hours. So there is no degradation of the technology and of the equipment. The projected lifetime of the membranes, conservative assumption is 7.5 years, but we think it can be expanded by up to 15 years thanks to further improvements in the future. Of course, a power plant needs power itself to pump the water through the pre-treatment systems, with this rapid sand filtration, and to pump the water through the membranes in the membrane stack. And this power consumption is about 25% of the generated power. So we generate 75% efficiency. Our pilot plant, as I said before, is located in the Netherlands, a very sensitive area, especially the saltwater side, the sea, is a nature protected area, UNESCO protected, so we have to be very, very careful not harming everything. The flora and fauna must show no mortality. It is monitored by the Dutch Institute Deltares and NIOS year-round and extrapolated to a large full-scale plant, and there is no mortality at all, so we're really good to go in a sensitive, nature-protected area. That means that we can do it there, we can do it everywhere. And it's from contracting point of view, it looks more like a water treatment plant than like a power plant. It's a membrane plant, so we have the normal operating cost and on maintenance. For background is, as I said, by the Wetsus Institute. In the Wetsus organization, 18 PhDs have been working on this. We're working on several European founded contracts with a whole bunch of institutes, mainly in Europe, and a total more than 50 million euro has been invested to this technology. I mentioned already that compared to solar and to wind, our process is full continuous, so not needing batteries, not needing conversion and storage systems. Let me say something about the cost. At the moment, our pilot plant is, of course, way too expensive per kilowatt hours. We're the first one in the world, leading worldwide on the technology, so I don't even want to know how much a kilowatt hour from our pilot plant cost. But we made calculations and projections, what would it cost on the longer term at full-scale plant. The first full-scale plant built in Europe, 100 megawatt power plant, that the total investment would be at about 800 million euro. And well, you calculate that down to the finance cost, operating, replacement, and so on, according to the ARENA model, the kilowatt hour price of that first full-scale plant in the Western world would be between 11 and 12 euro cents per kilowatt hour, or 11 or 12 dollar cents per kilowatt hour. Once we go down the cost curve, maybe after 6 or 7 full-scale plants are realized, it is calculated by Dutch TNO and reported to the Dutch government, supported also by other consulting engineers. The price might go down to 5 euro cents per kilowatt hour or 5 dollar cents per kilowatt hour for full continuous power. In India, why did we come to India? I think there is a strong tendency in the energy transition and we need a wide energy mix. The government and the power companies are showing good leadership in this innovation into the transition. So although we are a small company, we can select only a few countries in the world to zoom into, and one of these countries, of course, is then India, next to Spain and the Netherlands. There are many rivers in India. That's good. The temperature is pretty high of the water. So in India, the potential is about 114 gigawatt once our technology would be fully implemented. A list of rivers, we have quite a documentation elaborated. It's available in the booth, 70 meters in that direction. There is the Dutch pavilion, where we have a part of that booth. We have quite an extensive document available explaining the technology, but also explaining about the financials and the potentials of the technology. I said we are pretty famous already in the Netherlands, and now we are opening and trying to get foothold in India. We have created Redstack India, we are close in Delhi, and we are ready to build up a pilot plant either with the Institute or with Ministry or with power companies, and hope to do that this year so that we really then can introduce this technology into India. In Europe, we got a lot of political backup. This technology is officially confirmed to be a renewable energy by the European Union, followed by all the national entities. And so far, so good. We got good feedback from the Ministry of New and Renewable Energy that they want to support and push this technology to make it in India and contribute in the energy mix. That's it for now. Thank you for your attention and hope to see you later in our booth to elaborate on this. Thank you.
Thank you, Peter. It's indeed a very interesting presentation and a very innovative solution. Never heard like saline water can generate renewable power. We'll be happy to explore it more. So now can I request Nick Borisov to come over stage and present his paper on unlocking decarbonized, affordable and reliable electricity for India's industrial growth.
Thank you all. Thank you to the hosts ministry as well as the delegation present here and the organizers of the event to give me the opportunity to present to you a novel methodology of producing decarbonized power using various feedstocks in a way that we inherently capture carbon dioxide and utilize it for a purpose of producing energy. So we'll get right into it. A little statement from our attorneys, but just to give everyone some context into Eight Rivers, we are a pure play clean energy company. We founded over 16 years ago on the premise that energy had to be affordable, reliable, secure, as well as decarbonized. And that was the foundation for all of our product lines that came after our original invention, which I'm here to talk to you about, which is the alum FETVET cycle. And over that time frame, we've been very successful in obtaining several patents along the way, and we are now moving into the commercialization phase. So I'll be able to give you a little update on the development work that's being done currently. We are housed in Durham, North Carolina in the United States, and we also have an office in Houston. So this gives you an idea of our portfolio, and I'll just quickly run through this for the sake of time. But I'll be talking primarily about the alum FETVET cycle. We essentially carved out two different marketing pathways just based on the way the market is trending, which is to have a part of the product line that's focused on biomass and another that's focused on conventional fuels such as coal and coke, because we believe that the way to achieve energy security and prosperity is by decarbonizing affordable energy sources. And from that core technology, we took that and we adapted it using this process of inherent carbon capture to also produce hydrogen. We utilize the same looping technology to develop a direct air capture technology, a sour gas sweetening and decarbonization platform, and we've partnered with a company, KC8, based in Australia, that does a non-amine-based post-combustion carbon capture. Oops, sorry about that. Just a little, sorry, it's jumping around on me. Just to give some context, as a technology developer and project developer, we rely on the local resources of the economy that we're working in. So part of my ambition in being here today is to meet with counterparties that can help us develop projects in India using India resources. So it just gives you an outline of the way that we sort of fall into the value chain between feedstocks and producing commodity products, low carbon commodity products that can be value added in the market. And just to give some further context, you may know some of these numbers already, but as many of you know, the expected peak demand for power in India is just expected to grow tremendously. A lot of that is being driven by a number of factors, but some notable factors include the development of data centers, EV build out, as well as green hydrogen. All require not only power generation, but dispatchable base load. And if we pick this apart and look at the peak demand, some interesting factors start to show up here that we've also seen in the United States and in the European markets, which is that if we look at the generation capacity today in India and we carve out the critical base load of coal and the current amount of intermittent solar and wind renewables available in the grid, what we find is that over time, as you move towards this ambitious goal of reaching 2,100 gigawatts available by 2047, that we start to develop, you see in the bottom right corner, what's called the duck curve. And if you're not familiar with the duck curve, it has to do with the intermittency of renewables on the grid and what other countries and states have figured out is that as you develop those renewable resources, you need to develop the base load that goes along with it, because companies can't function, industries can't function on intermittent power. So obviously we have this two sort of competing goals that can sort of help each other or tear each other down, decarbonizing the energy, but also developing economically. So that translates to, setting up the scene for novel technologies such as ourselves to provide that gap for the renewables. So let's get into the technology, and I'll walk you through the various steps of it. But keep in mind that the goal here is that we believe that energy sources need to be available in various different forms. They need to be affordable and also low carbon. So just as we think through this, like I said, this is not the solution to every challenge that we have in the market as far as the availability of power, but it is a necessary component of it. So let's look at this Alm-FETVET cycle or AFC technology. So what are we doing in this case? We're essentially utilizing natural resources, so that could be a biomass, woody biomass, it could be municipal solid waste, it could also be coal or coke, any type of carbon dioxide generating fuel, and essentially using the gasification step to produce syngas and heat. And in doing so, we produce a stream of carbon dioxide. And what we do with that carbon dioxide, because it's now very chemically stable, is we can use it to now generate heat and transport heat, and we can also use it as a motive fluid to, in this case, drive a turbine. So what we're effectively doing is pre-combustion, so rather than trying to capture carbon dioxide on the back end and treating it as a contaminant, we're effectively utilizing it as a resource. And I'll get into the cycle a little bit more. So let's break this down a little bit. From the traditional power cycle, we generally use, in an air-breathing gas turbine, we draw in ambient air, which has a number of different components to it, including nitrogen, oxygen, and other contaminants. And then on the backside, we have this blend of contaminants in the flue gas that then we have to separate out, and then take the carbon dioxide from a low concentration, increase that concentration to near 100%, and then remove it from the system. In the AFC process, we essentially change that dynamic by utilizing oxycombustion to generate pure CO2 and then use that CO2 to drive the turbine. So in the end, what we're left with is pure CO2 that we have to deal with. So if we look at the development curve of the technology, since the technology was first founded in 2009, we effectively spun off a separate company in 2010 called Net Power, which fast forward to 2023 went public on the New York Stock Exchange with the help of Oxy and the Rice brothers, and it's now managed by the former president of EQT, Danny Rice. And with that, they are separately developing this process with using natural gas as the feedstock. So we continued to develop the technology, built a 50 megawatt demonstration facility in LaPorte, Texas, that we utilized originally to test out the concept of CO2 capture and looping back to the front of the process, which we successfully did. And from that point forward, continued to do work on the combustor design, and have now established a partnership with Siemens Energy to develop the turbine to support the CO2 capture. So just very high level, this is what the process flow looks like. So essentially we take a feedstock, we gasify that to produce syngas, and then we add oxygen through air separation unit to produce a stream of hot CO2. And what the lines represent here is relative mass flow. So as you can see, due to the fact that we want to capture as much CO2 as possible and utilize it in the loop, that a majority of it is kept within the loop, so a very closed system for the most part. And we take that those components through the combustor into the turbine, and we utilize that to drive the turbine. And then the rest of the process is frankly just recovering heat from that residual CO2 and then sending it back, compressing it, preheating it, and sending it back to the front of the combustor. So this gives you a little bit more definition around it for the engineers in the room. But effectively, if we start from the preheat step, which is in the bottom left, of taking a gasified heat component, mixing that with the syngas that's at the top, along with the oxygen from an air separation unit, effectively we send that mix into the combustor and circulate it until we reach a supercritical state for the CO2. And then we drive the turbine to produce power, recovering all of the CO2 on the back end. So as you can see from this diagram, by the cycle, that we are recovering near 100% of the total mass volume of CO2 to loop back to the front of the process. This diagram shows you a rendering of what the facility that we're currently in development it looks like. So we've established as our first project in the United States a project that was announced with the public utility in the western U.S. To develop essentially about a 230 plus megawatt electric facility based on the original work that was done at LaPorte. So the novel part of the process, which was the capture of the CO2 and utilizing it, recovering it back to the front of the combustor, has already been proven. So the next step for us is to just do this with essentially with a gasification kit on the front end to produce the syngas. So this just gives you some of the statistics around it. It's a commercially viable facility, and the way that we look at this is that it's going to be very difficult, if not highly unlikely, that anyone would build a new construction coal-fired generating station in the future without carbon capture. So the way that we look at this is, if you're going to build it and we still are going to utilize it as a natural resource, then do it in a way that inherently builds in carbon capture into the facility, and you can repurpose existing sites that are set for retirement or demolition and repurpose that site to continue to produce base load power for the next generation. The other thing that I'll point out here is that this is not exclusively any particular knock on renewables. In fact, there's a lot of synergies here. The fact that one of the downsides of hydrogen production is that it produces, in the case of electrolysis or solid oxide electrolytic cells, produces a significant amount of oxygen. That significant amount of oxygen could be used in our process to help us on the oxy-combustion side. So there's actually a lot of opportunity to use both energy sources to produce additive power that we can put to the grid. So a final just a roadmap in the way that you can think about us. The AFC process itself is not a retrofit kit. It's nothing that we can add to an existing facility. It has to be built as a greenfield site. But one of the ways that we look at this, and part of our partnership with KC8, is that don't bring amines onto your facility, because there's a number of reasons not to do that. But if you're going to do it in a stepwise fashion. If you can retrofit the site with a lower cost methodology of capture, you can add KC8 until it's time to retire that facility, and it gives us the opportunity to build out new construction AFC process and utilize the existing resources. So thank you all for your attention, and I'll be available after the session.
Thank you, Nick. Very interesting. Now can I call upon Nitish Kumar, Lead Application Engineer, GE Consulting. His topic is a data-driven approach for optimal selection of thermal plants for MTL flexibilization. So Nitish, over to you.
Thank you, ma'am. Good afternoon, everyone. I think context has already been set. With the end aim is to decarbonize our energy system, and all we are doing is to accelerate this process to it more efficiently and economically. So, with that, let's start our today's presentation. The topic is a data-driven approach for optimal selection of thermal plants for MTL flexibilization. Here, MTL is the minimum thermal level. It's the constraint on the unit's generation level, below which a unit cannot generate. And in the coming slides, we will understand how it's affect the unit operation, the grid operation, and the overall RA integration in the system, which is closely related to the decarbonization process. So in my presentation, we'll start with the understanding the test system, which is India. We are working on the India system, and we will try to understand the problem statement. We will look at the different solution options and how we selected the MTL for our research work. We will also discuss the tools which we have used in this study, and finally the takeaways from the study. So this work is part of a larger study which we were doing for a customer, and our test system is India. As we already know, India is the third largest electricity market in the world based on the total energy consumption. However, if we look at the per capita energy consumption, it's still very low compared to the other developed countries. And with the all industrial and economical growth, this is expected to grow significantly. We have two baseline years in our study, 2022 and 2020-30. So 2022 is already we have experience, we have the data, and with our tools we are projecting the grid operation in 2030. So in 2022 we had overall energy consumption in the country of about 1500 terawatt hour, and in next 7 years it is expected to grow to level of 2400 terawatt hour, which is about 60% increase from the 2022 level. India has also commitment to reduce its emission intensity in the power sector, and the target is to reduce the emission intensity for GDP by 45% by 2030 from the 2005 level. So now we have two challenges here. We need to meet the growing demand, and we also need to reduce the emission intensity from our electricity market. And how to solve these two problems simultaneously? So the answer is we need to increase production from the sources which are less polluting. Mainly in India, we are more focused on the solar and wind energy, and their output is variable in nature. They pose some challenges in grid operation, and we will see through our projection, through our modeling work, how we are facing those challenges and how we are taking care of that. So if we try to understand the severity of the change India electricity market is going to see, we will compare two-year simulation data, so 2022 and 2030. In 2022, if we see the installation mix in India, in left hand side we have the absolute megawatt numbers, and at the right hand side we have the installation mix at 100% of scale. So in 2022 we see the almost more than 50% of the installation base comes from the coal technology. We have about 100 gigawatt of renewables in form of solar and wind, and 47 gigawatt of hydropower. The balance requirement for the solar and wind technology is being complemented by hydro, gas turbines, and the pump storage. So in 2022 we see a very good installation mix to manage the variable renewable sources in the grid. But when we look at the 2030, the plan for the country to phase out the coal units, add the new coal units, meet the new targets for having the 500 gigawatt of non-fossil fuel based generation, we are seeing about 425 gigawatt of 425 gigawatt of solar and wind capacity by 2030 in Indian grid. We will also have significant coal by 2030. The total capacity projection is about 234 gigawatt, and we are projecting a battery capacity to manage the variable renewable sources in the grid for about 42 to 45 gigawatt. If we look at the transition from 22 and 2030, whatever the new capacity is coming in the grid, almost 75% of that new capacity is coming in the form of solar and wind. These resources are weather dependent, their output are variable in nature, and they need balancing power to have a secure grid operation. That balancing power we get through storage in form of battery or PSH, dispatchable units like thermal, and also a very good balance we get from the hydro. Yeah, so in 2030 when we have so much solar and wind, the question arises that how to manage that level of high renewable penetration in the grid. Because the solar comes when it comes, the wind energy we get when wind blows, and but our load interaction with these renewable generation sources are different. So we need balancing power, we need the flexible generation in the grid to manage that point. And here in the left hand side we have shown what we call is a flexibility fruit tree, and the fruits we have hanged is based on the cost at which they come and the effort at which they come. And typically we see when we need those flexibility fruits, we just pick the lowest hanging fruit. And if we discuss about these flexibility options in the grid to manage the high renewables, we can have a new storage in the system in form of PSH and battery. We can have new generation technology which are fast acting. They can respond to renewables generation very quickly and help accommodate them in the grid. We can have new transmission system so that we can share that power with our neighboring states, neighboring countries. We can provide the larger balancing area for these variable renewable sources. We can have a very good ancillary services through market to try to balance that power. We can also integrate demand side management. We can have the faster market to so that customers and generators can respond to these changes very quickly and balance in real time. And if we have too much variable sources, we have to curtail them. They come at some cost, but we can curtail them to have a secure grid operation. When we look at further down the line, we can have coal units having two-shift operation. During the peak generation hour, we can have the unit shut down and again switch on during the peak demand hour to get the power. And we also have one option, which is the topic of today's discussion, is to have the coal more flexible from the minimum thermal level side. So currently in our country, we have a minimum thermal level of coal units at 55% level, and there is a discussion going on to bring that to at 40% level. So in next slide we will see how this additional flexibility help us integrate more renewable in our grid. So the minimum thermal level is actually a constraint on the unit generation below which a unit cannot generate. So unit generate between its MTL and the max capacity level. Whenever load comes, it will increase its generation to cater that load, and whenever renewables comes in abundant, it will just reduce its output to accommodate that power. But they cannot reduce their power below the MTL level. And if we have a more flexible unit from 55% to 40%, we get the additional 50% of the bucket, where we can reduce the thermal output by that amount and accommodate that power. And that way we can have the more RE in the system. In the same line, when CA has the shared guidelines to the different coal units, coal power plants to have the upgrades and reduce their thermal minimum to 40% level. We were asked the question that we were asked two questions. First, is it really required to have all coal units to the 40% MTL level unit? And if we want to, and the second question was, if we want to do this in phase-wise manner, what should be the priority list of those units which should be made flexible? So where our investment should go first. So this, we are taking this as an optimization problem, how to extract the maximum benefit with the limited investment we have in this technology. Our third interest in this was to develop a framework to provide the consultancy work in this domain. And for this work, we are using two tools. One is our existing offering by G Vernova named PlanOS. This tool is widely available. This is a proprietary tool from G Vernova, but commercially available to use for the customer in all over the world. Mainly, it was developed in early 1970 to do the generation and transmission planning studies. However, it evolved to PlanOS level, and it can cater all aspects, almost all aspects of the electricity market. Basically, PlanOS is a linear programming, security constrained linear programming model, and at hourly, at sub-hourly level, it based on the merit order, it dispatch all the units to have the secure grade operation at minimum production cost level. We have been using this tool to generate spot prices at node level, to project units performance, to evaluate the standard investment, identify the congested lines in the transmission system, the costing of that congestion, and we are also using this to quantify the policy changes in the electricity market base for the unit on the unit's revenue. So we have used this tool to simulate 2030 grid operation in India, and then we developed another Python-based framework to get the priority list of thermal units, which should be in the candidate list for their MTL flexibilization. So we are simulating this grid in our grid, India grid for 2030 in PlanOS, and then that solution file is being read by our new Python-based framework. So first, it creates the candidate list. We have almost 600 coal units in the system. It creates the candidate list, the area-wise curtailment at sub-hourly level, and then it performs a calculation which is highlighted here. So first, it picks one unit. It sees how it's operating for every time block in the whole year, and for those time blocks, what is the curtailment level in that area. Then it virtually reduce that MTL level to 40%, and then try to accommodate that curtailed RE in that time block with the additional bucket it has created. Now with the additional RE integration, we have the reduced power consumption and reduced power generation, and so we save in fuel and the BOM cost. That this tool reports as a saving for this MTL reduction. After doing this calculation for all the candidates units, it sort the units in from the highest to lowest cost reduction, and then pick one unit to have in the priority list. Then it reduces that curtailment level for according to that unit, and then does the same operation for now n-1 unit for the same loop. So this algorithm works like sorting the bubble algorithm, very similar to the sorting the bubble algorithm, and then finally it gives a priority list of coal units which should be prioritized in that order to have the MTL flexibilization upgrades. So after this exercise, we had a priority list, and when we looked at the priority list, we are seeing many coal units. They are not offering much reduction, much benefit in form of reduced production cost. So that actually gave answer to the first question, and that was, do we really need um, to have all coal units upgraded to 40% MTL? And then to answer the second question, we selected top 80 gigawatt of coal units for MTL flexibilization panels, and we again ran our plan OS model for two cases. In first case, we are running the case with all units at 40% MTL, and then in second case, we are only running the model with 80 gigawatt of coal units at the 40% MTL, and then we are comparing the production cost saving from the base case. What we are saying, when we had all units at 40% MTL, we are saving total of about 8,000 crore, and when we had only about 80 gigawatt of coal units at 40% MTL, we are saving about 6,000 crore. So, so our finding was, if we use the diverter-driven approach and pick the units smartly, even with the 35-40% of the total fleet, we can actually achieve a significant amount of saving compared to just doing the upgrades for all coal units. After changing the level from 55% to 45 level, if you want to see how the units has operated, in the left hand side, for 2 days we have shown the operation. During the curtailment hour, now unit is generating less and trying to accommodate the VRE in the system, and the LDC is actually showing how much additional RE it has absorbed in the system with this benefit. At the system level, we have also quantified that benefit at the system level, and we are showing the dispatch of those 80 gigawatt units which were made flexible at 40%, and we can see during the curtailment level, they have at aggregate level, they have generate less and try to accommodate the renewables in the system. So with these 80 gigawatt of additional flexibilization, we are able to reduce overall curtailment by 2.5%, and the overall saving number is about 6,000 crore. So in summary, if we choose the units smartly, even with the 35 to 40% of the total fleet, if we made more flexible to 40% level, we can have the most of the benefit rather than doing all the units at 40%.
So, Nitish, I'm sorry, you have
Thank
to
you.
wrap up quickly.
That was my conclusion.
Okay.
We can connect later for the questions. Thank you.
Sure. Thank you, Nitish. Now, can I call Amit Sinha, Data Center Program Lead from Electrical Fluoro Daniel India. He is going to talk about the challenges and solution in design modeling, clash coordination and execution in bus duct package owing to space constraint in data centers. So, more on the technical aspects of data center and how efficiently these design and modeling can help meet the challenges. Over to you, Amit.
Can you imagine that even a small 10 to 15 megawatt data center can have bus duct length of more than half a kilometer? Truly speaking, if not handled well, bus ducts have potential to come into the critical path of the project and delay the data center project. Good afternoon, everyone. I'm Amit Sinha, and I'm here to present the design challenges in handling the data center package in bus ducts in data centers, and solution and mitigation plan for that. Data centers have seen unprecedented growth, and fortunately, I have led 4 data center projects in the country for the last 3 years. So this presentation is drawn from that. So in India, it is quite established why bus ducts are preferred over power cables. Bus ducts are compact. They can help you in faster installation. They are safer for operations. They are safer for maintenance. They have a low fire load. They have lower electromagnetic interferences, and some state regulation mandates usage of bus ducts over 750 kVA of power distribution equipment, if it is transformer or DG. Can you imagine that the fire load of bus duct is 1/10th of PVC cable and 1/30th of PE cable? This is how much the bus ducts are safe. There are some pictures of bus ducts which you must have come across earlier also. Now there are some useful features of bus ducts which makes it very
Good
apt for data
afternoon,
center.
ladies and gentlemen. We welcome you to third edition of IEW 2025. The show timings for today are from 10 a.m. to 6 p.m. All visitors, exhibitors, and delegates are required to wear their badges at all times. Children below 18 years will not be allowed inside the halls. Please take care of your belongings. Thank you.
Yeah. Yeah, so there are some useful features in the bus duct that makes it apt for data centers. The first is cable tap-off box and feed unit. These can be installed on bus ducts, which even if the bus ducts are energized, and this can help you to take power to any load, of any corner of the data center. T-offs. Data centers, especially large data centers, are not established in one go. They are established phase-wise to align the capex with the IT revenue generation plan. So these kind of T-offs are installed at the phase boundaries, which can help you in seamless expansion of data centers. Then there's something called copper to aluminum interface box, which converts copper to aluminum and saves cost. Then you have angular elbows, combination elbows that makes the bus duct maneuver in a very small area without any joints. Now we come to the slide which talks about inherent complexities in bus duct in data centers. Unlike other industries, in data centers, the electrical room or substations are on every floors and at multiple locations. Apart from that, the transformers and DGs can be either indoor or outdoor. Adding to that, the DG and the UPS also need constant testing. So it also requires a permanent setup of bus ducts from the UPS and the DG to the load bank. So all these things make the bus duct travel across length, breadth, and height of the building, and it makes it a very intricate network. Apart from this, there are many services in the data centers that goes along with the bus ducts, which are HVAC ducts, HVAC pipes, fire water lines, chill water lines, refrigerant pipings, cable trays, containment, security containment, telecom cable trays. So all these things go in parallel to the bus ducts, which makes it very, very challenging to do the designing. Apart from that, you can see there are vertical clearance requirement in every corridor that also has to be factored in. Plus bus duct adapter boxes. Putting adapter box in whose scope is also a challenge. No vendor wants to own this scope, but it is the EPCM who has to fix it and take it forward. Then another challenge that we find in data centers is construction of bus ducts of data center in tranches or in phases. So what happens when you install the challenge here is that the phase 2 or phase 3 bus ducts or any services which are to be installed, if it is coming above the phase 1 bus duct, then there are a lot of challenges in construction sequence, safety of construction, taking care of safety of the bus duct energized in the first phase while you are doing the construction of second phase, okay, and avoiding shutdown in the construction of second phase. So all these things have to be taken care during the design itself. So these were the known knowns. Now we come to the known unknowns. Manufacturing tolerance in bus ducts, these are known unknowns. Bus duct clashing with supports of other services. While you can manage the clash between bus duct and other services, the support of other services can clash. Then mismatch between 3D model of the equipment with the physical drawing or the physical equipment. This also happens. Then construction tolerance. In this industry, the construction happens as per the model. We don't have coordinates in the drawings. So what happens? Because of that, the construction tolerance kicks in and the RCC width or column orientation or foundation grade or equipment placement have little bit of differences as compared to model. So this leads to the issues during construction. Then we have we have load bank bus duct which is 3-wire and power bus which is 4-wire. There can be mixing of both of these bus duct during design, and that can lead to discrepancy during construction. Then you have human error also during while fixing the phase changeover box. So now we come to the important slide about solutions to mitigate challenges and streamline execution in bus ducts. This slide talks about solutions to be implemented during engineering. BIM software, whether it is Tekla or Revit or Navisworks or Autodesk, both the parties, that the contractor, GC, general contractor, and the manufacturer shall have the same version of the same software. This will enable them to exhaustively review each other model and lead to avoid errors. Then copper to aluminum interface box. Yes, it saves capital, but it occupies big space indoor. So while you are saving on cost and construction timelines, you are also creating a lot of space constraints. So selection of this interface box must be done judiciously. Then termination box interface. The adapter box interface drawing needs to be signed off by both the parties, the manufacturer of the bus duct as well as the manufacturer of the electrical equipment. Then during modeling, when you do the model of bus duct, the construction tolerance should be considered, and if you have a clearance of 100 millimeter between bus duct and any other services, consider it as 0, because this 100 millimeter difference will vanish during construction. So it is always better to have differences, clash coordination with higher differences between the two services. Then manufacturers should be also suggested to manufacture small pieces, because the small pieces will help you to solve discrepancies during the final stage of connection of bus ducts. So that was the solution during engineering. Now we come to the solutions during procurement. So there is something called field fit program. In this program, you don't order the bus duct completely at one go. You order it in two or three phases. First phase is, the first lot is when the consultant does the issue for IFC drawings. That time you order 70% of the bus duct, and those are the standard pieces. After that, when the contractor does the re-coordination of the model as per the site condition and as per the actual physical dimension of the services, all the services, that time you order remaining 20 to 25%. During that time, it is also important to mark few pieces in every route as hold pieces. These pieces are to be measured at site after the installation of the complete bus duct and then ordered. So that is the third lot. So, so in the third lot, what happens? You install the first lot and second lot, and then the site measurement is done, and then the bus duct of the remaining, the XYZ axis are ordered. So how does it help? It helps you to have exact fit at the first time. It helps you to effectively manage the dimensional uncertainties. There's so many variables we have seen. Everything gets solved with this methodology of ordering the last lot after the installation. And also it takes care of your schedule, because you are already planned this. Now for this to happen, you have to ensure a robust supply chain system is there. You should opt for a local manufacturer who can deliver it very quickly. And also you can opt for reverse supply chain, where the pieces that don't get fitted should be given back to the factory. Now comes the solution to be installed during construction. So the construction team should be aware that the last 5% of the bus duct has to be ordered as per their input. So they have to install the bus duct early. Plus they have to install all those services which are required to install the bus duct early, like the bus duct supports, the source equipment, transformer, DG, or the switchboard. Everything has to be installed early so the bus ducts can be installed early. Second is the outdoor support for bus duct. Now you can see there are two photographs. The left one is bus duct in a wider support, and right one is the bus duct in narrow support. So these supports should be made little wider for the outdoor, because this takes care of the lateral shift of the bus duct when the bus duct comes from indoor to outdoor. Now these kind of supports are on the grade level, so it's not possible for them to be changed later. So if you plan it well, you will avoid changes in the underground when you install the bus duct in the outdoor. Then during construction, there is a margin of 6 to 8 millimeter in every joint that construction team should be utilizing during the installation of bus duct. So in a straight length, you can get a margin of 50-60 millimeter if you have 7 to 8 joints. So that helps in adjusting your bus ducts. Then canopies. Canopies of bus ducts, they look very simple, but they occupy good amount of space in outdoor. So canopies still can be made flexible owing to space constraints. Then this is very important, that when you design other services, the support of other services should not be over-designed. You can see chill water line, which has been designed in a support which is quite extravagant. Now this chill water line is tested already. Now bus duct is getting installed and bus duct is clashing with the supports. And you can't do anything with the chill water line because it's already tested. So support of other services should not be over-designed. Last point, that is laser scanning technology. This laser scanning technology is not a new technology, and it should be implemented when you install the 70 to 80% of the bus duct. This helps you to identify whether the remaining pieces of the bus duct will be exactly fitting or not. With this technology, you scan the plant, you scan the data center, and you check with the model of the bus duct whether these two are matching or not. So you basically do a proactive or a preemptive site measurement of the bus ducts, and in case you find any discrepancy, you order it before the bus duct schedule, before the time, I would say, before the right time. So it gives you a pre-advanced information. So now, with this we cover all the solutions to be implemented during engineering, procurement and construction of bus duct in data center. I hope the audience would embrace these solutions and implement this in any future design of bus ducts in data centers. Thanks to these suppliers whose catalog gave me a lot of information, which I added in this presentation. We are from Floor India. We are based in Gurgaon as well as in Baroda, and we believe in sharing knowledge and growing together. Thank you. Thank you, everyone.
Thank you, Amit. So with this, our session on utilities and power generation is over now, but I want to thank to all our esteemed panelists. Today we discussed from power factor control to maximize renewable energy. We looked into how salinity of water can generate renewable power. We looked into adopting renewable power in industries in a bigger way. Also looked into data-driven approaches for flexibility and making optimal choices, and then going into the detail of data center, which is going to be a major power guzzler in years to come as we adopt more and more AI, how electrical solutions can be developed around there. All our panelists are available for a Q&A session, however, after this entire meeting. So now I thank all of you, and we look forward to the next session now. Thank you.